All right, we're going to pick up with reflections now. The graph of g of x equals negative f of x is the graph of f reflected across the x-axis. The graph of g of x equals f of negative x is the graph reflected across the y-axis. The difference between these two things is one has the negative out in front and one has the negative inside the parentheses. So that means that if I have a function like, say, f of x equals x squared plus 4, then if I'm doing a reflection across the x-axis, or negative f of x means that I do negative times all of it. So that's going to be a negative x squared, and then distribute the negative to the 4 as well. So minus 4. In the bottom one, if I'm doing f of negative x, that's g of x equals f of negative x, which means that everywhere I see an x, I put a negative x, which means it's going to be negative x squared plus 4. Negative x squared, because that's in parentheses, you're squaring the negative, so that's just going to turn right back into x squared plus 4. Now, does that make any sense? The reflection of x squared plus 4 across the y-axis, if we think about what that means, what that means is that I am doing my original x squared plus 4. If I flip this right half over, it's going to land directly on top of the left half, right? So that if I do negative x squared plus 4, it's the exact same thing. Which is why, whenever I solved that out, it ended up being x squared plus 4, because it creates the same graph. Is that always going to happen? No. In general, whenever anytime I have a new function like this, x to the third, whenever I make that negative x to the third, that's going to stay a negative. So that's equal to negative x to the third. If I graph those two, you'll see the difference here. X to the third looks like that, and negative x to the third is the opposite direction. Oops, got rid of the wrong one. So this graph in purple is different than the graph in black. And we can see that within our equation. They're not the same thing. Okay, graph g of x equals negative x inside the brackets. So this, you should recognize this as the step function we had, or the greatest integer function. If you remember all the way back here, this is our greatest integer function. So this is the original. If I'm looking at reflecting this over the x-axis, that's where I'm going to start. If I reflect it over the x, then everything that's up here comes down to here. So 0, 0, this line segment stays the same. Nobody likes Apple. So this is going to stay the same here. But now this is going to come down. This is for the first one. And if we think about what these numbers mean, what it means to reflect it over, it makes sense, right? If I'm saying that everything is going to become 2 between 2 and 3, right? Everything becomes 2 when x is between 2 and 3. Then if I have negative of that, everything is going to come down to negative 2. So does that one make sense? Now let's look at the next one for h of x. H of x is negative x, right? And so if I'm talking about from 0 to negative 1, it's going to flip it across the y-axis. So now it's going to be an open circle over here, and like this. That's close still. And then now this point comes over to the negatives, and it goes negative 2. And so on, and so on. If it's inside the function, outside the function, it flips it down over the x. If it's inside the function, negative, it flips it over the y. We're going to do plenty more examples of these. All right, vertical stretches and compressions. If xy is a point on the graph of f of x, then xcy is a point on the graph of g of x, where we're taking c times whatever our value was for the original. If the number we're multiplying by is greater than 1, then the graph of the function is the graph of the original stretched vertically away from the x-axis by a factor of c. In other words, if I multiply by 2, it's going to be stretched out twice as long. Then if, I don't know why there's 2 ifs, but if c is less than 1, then the graph of c of f of x, c times f of x, is the graph of f compressed vertically towards the x-axis by a factor of c. So if I multiply by 1/2, then the graph will be half as high for each x that we have from the original. All right, So if we have 5 times x squared, by now you should know that x squared is a parabola. It goes like this. 0, 0 is our vertex. It goes up 1 over 1. Then if I go over 2, it goes up 4. And same thing in this direction. And so we have this U-shaped parabola. That's our parent function. Okay? So if that's my parent function, then if I look at 5 times x squared, it'd be easy to plot these points out if I just think of them. Do a little table here. So if I do -2, -1, 0, 1, 2. I'm going to do a third column in this table, as a matter of fact. I'm going to do x squared so you can see what points I just found, and then 5x squared. That'd be cool. That'd be real cool. So when I did -2 squared, that gave me 4. When I did -1 squared, that gave me 1. When I do 0 squared, that gives me 0. When I do 1 squared, that gives me 1. And when I do 2 squared, that gives me 4. In other words, that's how I got each one of these points. 0, 0, 1, 1, -1, 1, 2, 4, and -2, 4. Yes. Now when we look at doing 5x squared, I could go back to my original and just do -2 squared, which is 4, times 5 gives me 20. -1 squared is 1, times 5 gives me 5. 0 squared times 5 is 0. 1 squared is 1 times 5 is 5. And 2 squared is 4 times 5 is 20. I could have also just taken my parent function values for what would have been y, and multiplied each of those by 5, because that's what we're doing to the function. So now when I graph my vertical stretch here, it's going to be at 0, 0, so it stays the same. Then when I go over to 1, it's going to be up to 5. If I go over 2, it would be up off the charts at 20. And so this parent function is being stretched out into a much skinnier version of itself. That's what some people think should happen to me. Vertical stretch. Oh, you Russellites out there like that one. Just kidding. You guys are Russellians. Because every day you're rustling. Stop. So anyways, this is a horribly drawn version because it's hard to do on this thing, but it makes it 5 times skinnier than what it originally was. So it's stretching it upwards by a factor of 5. And now we're going to start combining things here. So now I have 5 times x minus 3 squared. So now I can do multiple transformations to this thing. Let's think of the parent function again. Parent function is x squared. It shows it 0, 0, 1, 1, -1, 1, and 2, 4, -2, 4. If I wanted to keep going, I could go up 3, up 9. Just showing off now. And so this would be my parent function. Now, for each one of these, I don't want to have to create a table and graph each one. Like create a table, find my parent function. If I know what my parent function is, then I know what each of these transformations does to it. What does this minus 3 do? It's inside the parentheses, so it's a horizontal shift. It shifts the entire thing to the right by 3 units. Then the 5 out in front of it all makes it a vertical stretch. So it stretches it up 5. So now instead of being over 1 and up 1, it's over 1 and up 5. And this is my new graph. Close enough. I almost hit that point. Just make it a little thicker here. Did it. I would love one, actually. Somebody just offered me a cookie, and if they don't give me one, their grade will suffer. I don't care that we're not even in school. Get it to me somehow. There's actually, for those of you who want to know, there's actually a company called Cheryl's. Cheryl's is the sponsor of today's video. If you go to Cheryl's and enter the enter the promo code Russellin, you'll get a 20% off discount and a free cookie. But Cheryl's will deliver fresh cookies to your home. Their sugar cookies are absolutely delightful, and I love the chocolate chip. Cheryl's is making a paid promotion for this program. All right, so did everyone